Helium, the second most abundant element in the universe, has a fascinating origin story. It all began billions of years ago with the Big Bang. The immense heat and energy of this event created the first atomic nuclei, including helium. Stars are giant balls of hot gas, mostly hydrogen and helium. Inside these stellar furnaces, nuclear fusion occurs. Hydrogen atoms combine to form helium, releasing tremendous energy in the process. This energy is what makes stars shine and provides the light and warmth we feel from our sun. Over billions of years, stars exhaust their hydrogen fuel. As they age, they produce more and more helium. Eventually, some stars explode as supernovas, scattering their elements, including helium, into space. This scattered helium, along with the helium created in the Big Bang, forms the basis of the helium we find on Earth today. It's a remarkable journey from the heart of a star to our planet. Helium is known for its unique properties, one of the most notable being its incredibly light weight. It's the second lightest element after hydrogen. This lightness is what makes helium-filled balloons float. The helium inside the balloon is much less dense than the surrounding air, causing it to rise. Helium is also colorless, odorless, and tasteless. You can't see it, smell it, or taste it. This makes it safe for use in various applications, like inflating balloons for celebrations. Another remarkable property of helium is its extremely low boiling point. It's the lowest among all elements, remaining a liquid even at extremely cold temperatures. This unique characteristic makes helium invaluable in cryogenics and scientific research. Helium is also an inert gas, meaning it doesn't readily react with other elements. This non-reactive nature makes it safe for use in various industrial and medical applications where chemical reactions are undesirable. While we often associate helium with party balloons, its applications extend far beyond celebrations. Its unique properties make it essential in various fields, from medicine to aerospace engineering. One of the most critical uses of helium is in magnetic resonance imaging (MRI) machines. These machines use powerful magnets and radio waves to create detailed images of the human body. Liquid helium's extremely low boiling point helps cool the superconducting magnets in MRI machines, enabling them to generate the strong magnetic fields required for imaging. Helium is also crucial in scientific research, particularly in cryogenics, the study of materials at very low temperatures. Its ability to reach extremely low temperatures makes it an ideal coolant for various scientific instruments and experiments. The aerospace industry also relies heavily on helium. It's used to pressurize rocket fuel tanks, ensuring a consistent flow of fuel during launch. Additionally, helium is used in purging and leak detection systems in spacecraft and rockets due to its inert nature. Section 4. Helium's cousins, isotopes and their roles. Like many elements, helium exists in different forms called isotopes. Isotopes are atoms of the same element that have the same number of protons but differ in their number of neutrons. The most common isotope of helium is helium-4, which makes up almost all of the helium found in nature. It has 2 protons and 2 neutrons in its nucleus. This isotope is primarily responsible for the properties we typically associate with helium, like its lightness and low boiling point. Another isotope, helium-3, is much rarer and has only 1 neutron in its nucleus. This makes helium-3 lighter and even more valuable for specific applications. Helium-3 is used in cryogenic research and has potential applications in future fusion reactors. Although helium-3 is rare on Earth, it's found in greater abundance on the Moon. This has sparked interest in lunar mining as a potential future source of this valuable isotope. Section 5. Helium's scarcity, a precious resource. While helium is the second most abundant element in the universe, it's a finite resource on Earth. Its lightness makes it challenging to trap and contain. Once released into the atmosphere, helium escapes Earth's gravitational pull and drifts into space. Most of the helium we use comes from natural gas deposits, where it's found in small concentrations. These deposits are formed over millions of years from the radioactive decay of uranium and thorium. Extracting helium from natural gas is a complex and expensive process. The increasing demand for helium, coupled with limited production and inefficient recycling, has raised concerns about its availability in the future. This scarcity has led to price fluctuations and calls for responsible helium use and conservation. Section 6. Helium's future conservation and innovation. As we move towards a future where resources are increasingly precious, it's vital to address the challenges posed by helium's scarcity. This involves a two-pronged approach: conservation and innovation. Conservation efforts focus on reducing helium waste and improving recycling methods. This includes developing more efficient ways to capture and reuse helium in various industries like MRI and scientific research. Raising awareness about the importance of helium conservation among users is also crucial. Innovation focuses on finding alternative materials and technologies that can replace helium in certain applications. For example, researchers are exploring the use of other gases for cooling in some cryogenic applications, and developing new magnet technologies that don't rely on liquid helium. The story of helium is a fascinating journey from the heart of stars to our planet. Its unique properties make it invaluable in numerous applications, but its scarcity demands responsible use and exploration of alternatives. By understanding the importance of helium and actively participating in its conservation, we can ensure its availability for future generations and continue to benefit from this remarkable element.